Assalamu alaikum. My name is Abdullah Jangi, registration number 21TE11. Today I am going to explain the digital signal processing lab number 8. Lab title is FIR Filters. The objective of this lab is to implementation and analysis of moving average filter, implementation and analysis of finite impulse response filter Fourier transform design method. Basically, task 1 is define filter. A filter in the context of digital signal processing refers to a system or algorithm that modifies the characteristic of a digital signal. Filters are used to extract, enhance or suppress specific components of a signal based on their frequency, amplitude or phase properties. Types of filter. There are many types of filter. Number 1, low pass filter. Low pass filters allows frequency below a specific cut-off frequency to pass through. Attenuates frequency above the cut-off frequencies, used for removing high frequency noise or extracting low frequency components. Number 2, high pass filter. High pass filters allows frequency above a specific cut-off frequency to pass through. Attenuates frequency below the cut-off frequency, used for moving low frequency noise or extracting high frequency components. Number C, band pass filter. Band pass filter passes a specific range of frequency concentrated around a certain frequency, attenuates frequency outside the specific bandwidth, used for isolating specific frequency bands in signal. Number D, band stop filter. Band stop filter is also known as notch filter. Attenuates a specific range of frequency while allowing frequencies outside the notch to pass through, used to remove interference or unwanted frequency components. Number 3, what are the time domains parameter for a filter? Number 1, step response. Step response divided into two components, good and bad. Now, a good step response indicates that the filter settles quickly and smoothly to its final steady state value without significant overshoot or isolations. This ensures that the filter accurately tracks changes in the input signal and responds promptly to signal transitions. Bad, a poor setup response may exhibit slow settling time, excessive overshoot, undershoot or oscillations. These can result in signal distortions, inaccuracies in tracking input changes and instability in the filter's behavior. Overshoot. Good overshoot. A low or negligible overshoot is desirable as it indicates that the filter output closely matches the desired response without significant deviations or transient effect. Bad. Excessive overshoot can lead to signal distortions, ringing or instability in the filter's output. Linear phase. Good linear phase is considerable beneficial as it ensures that all the frequency components of its input signal experiences the same phase shift, preserving the signal's waveform and avoiding phase distortion. This is particularly important in applications where phase coherence and signal fidelity are crucial. Bad. Non-linear phase response such as phase distortions or phase shift that vary with the frequency can lead to signal degradations, similarly or transient signals and altered frequency characteristics. Non-linear phase can introduce distortion that the effect or quality of the filter signal. What are the frequency domain parameters for a filter? A good roll-off refers to the rate at which the filter frequency response decreases from the pass band to the stop band. Bad, a poor roll-off implies a gradual or slow decrease in the filter's frequency response from the pass band to the stop band. Ripple in pass band. A good filter has minimal or negligible ripple in the pass band, meaning that the magnitude response remains relatively flat and consistent across the desired frequency range. A poor performance is characterized by signal ripple in the pass band where the magnitude response. Basically, task 1 is the theory based. Number C, poor stop band attenuation. A good stop band attenuation refers to the filter's ability to effectively suppress frequency outside the desired pass band, ensuring the unwanted signal, noise, and interference are attenuated or eliminated. Bad Poor stop band attenuation indicates insufficient suppression of frequencies in the stop band, allowing unwanted signal, noise, or interference to pass through, leak into pass band. Number 5. Discuss the role of low pass filter of a filtering design. The role of a low pass filter in the filtering design includes selecting desired frequency while blocking higher frequency, preventing aliasing in digital signal processing. Task 2 is a MATLAB code based task. In this task, we have to plot the signal in time and frequency domain along with its magnitude response. Basically, task is as x is equal to 1 column 40 is equal to 0. This is our source code. We generated source code. Basically, first we have to define the function, then we use this subplot command stem because it is create signals. We use this stem command, title, x label, y label, compute the Fourier transform the signal, x is equal to f of t, x, compute the magnitude response. We use this formula, then we use subplot command, stem, title, x label, y label. Here is our output. First signal in time domain, then magnitude response, the signal in frequency domain. Its part B is x is equal x into 41 column 120 is equal to 1. This is our source code. The code for all the tasks are same. Here is the output of these two tasks. Then moving toward next. Here's our source code. First we have to define the function, then we use this formula noise to x, then we use this plot command, title, x label, y label, then we use the magnitude response noise formula. Here is the output. Then next is x is equal x into noise x plus 0.5 red size x. First we have to define the function, then we add noise to x, then define this moving average filter coefficient, then applying the moving average filter, then we use this subplot command, title, x label, y label, then we use the Fourier transform to the filter signal formula. Here is the output. Then next task is apply 3 taps symmetrically around moving average filter on signal x noise and observe the time and frequency domain parameters. Source code. Here is our source code. First we have defined the function, then we add noise to x, then we moving average filter coefficient define, then applying moving average filter, then we use the plot command, then we use the formula to compute the Fourier transform of the filter signal, then we use the formula to compute the magnitude response of the filter signals, then we use the plot command. Here is our output. Moving toward next. Apply 11 taps symmetrical around moving average filter on signal x, move noise and observe the time and frequency domain parameter. Here is our source code, then here is our output. In this output there are 3 figures. First filter signal in the domain, then magnitude response of the filter signal and filter signal in frequency domain. Then we have to apply 25 taps symmetrical around moving average filter on signal x noise and observe the time and frequency domain. Here is our output. In this output there are 3 figures. Number 1 for filter signal in the time domain, number 2 magnitude response of the filter signal, number 3 filter signal in frequency domain. Number task 3 the repeat example 7.2 for 17 tap coefficient. Here is our source code. Here is our output, and here is our output graph magnitude frequency response. And repeat example 7.2 for 51 tap coefficient. Here is our source code. In this source code we first define number of laps is equal to 51, then cutoff frequency in hertz, then sampling rate in hertz, Then we use the formula to calculate the normalized cutoff frequency between 0 and 1. Then we define the formula to calculate the filter frequency using the Fourier transform. Then we use the display command to display the filter coefficient. Then we determine a transfer function using the filter. Then convert the transfer function to symbolic. Then define display. Then we use display command to display the transfer function. Then we use the formula to determine a difference equation. Then we use the plot command. Here is our output of the magnitude frequency response. Its part B is apply the filter made in part A to the signal X. Observe the change for signal X in time and frequency domain while varying the number of coefficient of the filter. Here is our source code and here is our output. In this output, first graph is the original signal in time domain, then original signal in frequency domain, then filter signal with 17 coefficient in time domain and filter signal with 17 coefficient in frequency domain. Task number 4 is repeat example 7.3 with this 7 tab and 7 tab. Here is our source code. First we define a number of tabs for the FIR filter. Then we define the sampling frequency, sampling rate, and lower cutoff frequency in hertz, upper cutoff frequency in hertz. Here is our output frequency response of the 17 tab FIR band pass filter.